Hello students, in our last class we have seen the topics about scalars, vectors and orthogonal coordinate systems. Two coordinate systems we have seen in our previous class. So those two were cylindrical coordinate system and rectangular coordinate system, and conversion from rectangular to cylindrical and cylindrical to rectangular we have seen. And we have derived the mathematical equation for differential length, differential surface and differential volume in both the cases, such as rectangular or Cartesian coordinate system and cylindrical coordinate system. Now let us move on to the next coordinate system, which is very important while analyzing the three-dimensional things, that is spherical coordinate system. So what do you mean by spherical coordinate system? As the name suggests, spherical means, what do you mean by spherical? Sphere. It is a three-dimensional globe-like structure. It is a three-dimensional ball-like structure. So in order to represent that three-dimensional sphere, so we need to have some coordinates. So those coordinates are r, theta and phi. What do you mean by r, what do you mean by theta and what do you mean by phi can be obtained by using this cross-sectional geometrical shape. Now let us consider three axes x, y and z, which are perpendicular to each other. This orange line represents the cross-sectional view of a sphere. It is a sphere, semi-sphere. Along the xy plane, we have taken a portion of it. That's it. We have taken a portion of the semi-sphere. Got it? Now, consider a point P on a sphere. Consider a point P on a sphere which is at a radial distance of r from origin and which is at a zenith angle from the x-axis theta, which is at azimuth angle phi from the x-axis. This is the coordinate of this point P. There are three parameters by which a particular point P on this sphere depends on. Such parameters are radial distance or radius of the sphere r, theta zenith angle with respect to z-axis, phi azimuth angle with respect to x-axis. Let me write here. What do you mean by r? R is the radius of sphere, theta zenith angle, phi azimuth angle. So what is the range of this? This varies from 0 to infinity. So theta zenith angle vary from 0 to pi. So this varies from 0 to 2 pi. Azimuth angle, which is same as the cylindrical coordinate system, which varies from 0 to 2 pi from x-axis along the xy plane. Got it? This is the representation of spherical coordinate system. These are the three parameters by which it depends on. Now let me write spherical coordinate system in terms of Cartesian coordinate system. Spherical coordinate system represented in terms of Cartesian form. How that can be represented? X, y, z. These things need to be represented as r, theta and phi. Interconversion is required whenever is applicable in our theoretical aspects. So we need to perform this. In order to do this interconversion between Cartesian to spherical coordinate system, we need to simplify this particular diagram. Let me write here. Okay, let me write this cross-sectional view here. You need to understand this carefully. Okay, this is y and this is x-axis. So let us assume an arbitrary point P, okay, which is at a distance r from the origin. Okay, let me write if I look at this point from the top view, if I look at this point from the top view, it appears here, so which is at a azimuth angle phi, which is at an angle of theta here. So this is exactly appears here if I look at this point from the top view. We are not looking it from the front view. If I look from the front, it looks like this. If I look from the top, it will be a point on xy plane, two-dimensional plane. Okay, now it forms an angle phi with respect to x-axis, and this line forms an angle theta with respect to z-axis. Now if this is r, then what about this distance and what about this distance? Tell me. If this is r, what about this distance and this one? This is equivalent to r cos phi and r sin phi. This is equivalent to r cos theta and r sin theta. So let me write here. So let me just correct this. Okay, these two needs to be parallel. This is r cos theta and this one is r sin theta. Parallel components, r cos theta and r sin theta. These are the resultants of this particular vector r. These are the resultants of this particular vector r. Now, if this is a vector, r sin theta is a vector, its resultant components are along x and y direction. Then this becomes r sin theta into cos phi, and this becomes r sin theta into sin phi. Okay, this component becomes r sin theta into cos phi, and this component becomes r sin theta into sin phi. Okay. Okay, is it clear? Now let me write here. X can be represented as r sin theta into cos phi. Y can be represented as r sin theta into sin phi, and Z can be represented as r cos theta. See here, Z can be represented as r cos theta. Got it? Now x, y, z components are represented in terms of r theta phi. This is the conversion from Cartesian to spherical coordinate system. Now we need to perform back conversion, that is r theta phi to x, y, z. In order to do so, you add all the three components, that is, so equation 1, 2, 3, if we perform these three things, then r is equal to square root of x square plus y square plus z square. We are going to get this one. Then what about theta? Second component is theta, which is obtained from this equation. Let me do the cross multiplication. This is z by r is equal to cos theta. In order to obtain theta, theta is equal to cos inverse of z by r. Now this theta should be represented in terms of x, y, z, not with respect to r. So replace this r by this equation. Therefore theta is equal to cos inverse of z divided by square root of x square plus y square plus z square. Got it? Now second component is obtained. This is the first component, and the third component is phi. How to obtain phi? So in these two equations we have phi component. Let us do y by x. Y by x is equal to r sin theta into sin phi divided by r sin theta into cos phi. These two components gets cancelled. We left with sin phi divided by cos phi. Sin phi by cos phi is equal to tan phi. Therefore, phi is equal to tan inverse of y by x. That's it. This is the third component. Now, by using these two set of equations, we can easily perform Cartesian to spherical coordinate system, from spherical to Cartesian coordinate system. We can do interconversion. Got it? Okay. Let us continue with the spherical coordinate system. In order to define differential length, differential surface and differential volume with respect to spherical coordinate system, we have considered this particular geometry. Now assume that you have a watermelon which is a spherical in shape. Okay. So what you usually do while purchasing a watermelon, whether the fruit is ripened or not, you usually checks by taking a cross section of that particular fruit, right? So in the same fashion, you assume that situation here. So this is a watermelon. You need to check the ripeness of that fruit. You need to bisect some portion of it and you need to identify whether it is ripened or not. In the same fashion, we have taken the differential area here on the sphere. The differential cross section is divided into three parts. One is with respect to differential radial distance dr, differential zenith angle d theta and differential azimuth angle d phi. This small elementary section has been represented in terms of these three differential quantities with respect to spherical coordinate system. Those quantities are dr, d theta and d phi. As usual, we used to consider a cubical shape. Cubical shape means we need to consider this part, right? A cubical shape we have considered. So in order to analyze this cubical shape, we need to have three different surfaces. That is enough. Front surface, top surface and side surface. Okay. So in the same fashion, we need to consider this surface. Okay. This surface and the bottom, this surface. We need to consider these three surfaces while writing the mathematical equation for differential surfaces. While writing equation for differential volume, what we need to consider? Length, height and breadth. These three components. While writing equation for differential length, which are the three quantities we need to consider? So differential length of along radial axis, differential angle with respect to z axis, that is theta, differential angle with respect to x axis, that is phi. Now let me write the equation for differential length, that is dl. Differential length of the spherical coordinate system is equal to dl, which is a vector which is represented as dl in terms of r plus dl in terms of theta plus differential length in terms of phi. Got it? These three are in vector format. Now this can also be represented as dl with respect to r into a cap r in vector form plus dl with respect to theta in terms of vector a cap theta plus dl with respect to phi in terms of a cap phi. This is the vector representation. Then what about dl into a cap r? What is dlr? that is dr. Here the small radial distance which is considered here is dr. Therefore this quantity can be represented as dr into a cap r plus, what is the differential length along this one with respect to theta? Differential theta is r into d theta. Why we need to consider r into d theta? Because see here, this distance is continuously varying from this point to this point. Hence this distance is dependent on the radius of this sphere. Hence we need to have the differential length with respect to theta is r into d theta. Why r comes here? Because this differential zenith angle d theta depends on r, radial distance of this sphere. Hence it is represented as r into d theta. Therefore dl theta can be represented as r into d theta into a cap theta plus. In the similar fashion, this azimuth angle is dependent on both theta as well as radial distance. See here, look at this, r into sine theta into d phi. See, this azimuth angle phi is dependent on radial distance as well as the zenith angle theta. Hence this elementary angle d phi is equivalent to this. Therefore dl phi is equal to r into sine theta into d phi into a cap phi. This is the equation for differential length in terms of spherical coordinate system. Now let me write the equation for differential surface. ds with respect to r is equal to, which one we need to consider? We need to consider this surface, because the vector which is coming out of this will be perpendicular to this course. This is a cap r. The tangential one is a cap phi, which is perpendicular to this is a cap theta. These are the vector representations. Okay. Now in order to obtain differential area along a cap r, since it is a rectangular form, length into breadth. What is this length? This length is equal to r sine theta into d phi. This breadth is equal to, what is this distance? R into d theta. Therefore ds in terms of r is equal to r sine theta into d phi into r into d theta. Therefore this can be represented as r square sine theta into d theta into d phi. This is the differential surface area for r. Similarly, differential surface area with respect to theta is, we need to consider bottom surface. For bottom surface, which are the things? Length into breadth. We need to consider length into breadth. This is dr, and this distance is r sine theta into d phi. This is dr into r sine theta into d phi. Therefore this can be represented as r into dr into sine theta into d phi into a cap theta. This can be represented as a cap r. Okay. Now coming to the third one, that is differential surface area along phi. This can be represented as, which face we need to consider? This one. This face I need to consider, side face. For this one, length into breadth. This face is equivalent to r into d theta. This one is dr. Therefore, r into dr into d theta into a cap phi. This is the differential surface area with respect to phi. This is the equation for differential surface area with respect to theta. Differential surface area with respect to r. Now coming to the differential volume. Differential volume is equal to length into breadth into height. That is r into d theta into dr into r sin theta into d phi. By solving this, differential volume is equal to r square sin theta d theta d phi into dr. This is the equation for differential volume for the spherical coordinate system. You need to remember the analogy of watermelon. While checking the ripeness of the fruit, you need to cut open some portion of it. That is the same analogy which we have used here. So the cubical shape has been considered in order to have the differential surface area along r, theta and phi components to obtain the differential volume V. So what do you mean by theta? Zenith angle with respect to z axis. Phi means azimuth angle with respect to x axis, where r is the radial distance of the sphere. These are the three components which is required in order to represent a spherical coordinate system. Okay.